Could an earthquake that struck beneath Hawaii without triggering an eruption still reveal something profound about the forces shaping the Pacific? What happens when an entire volcanic island chain becomes so massive that it bends the floor of the ocean itself? And how can a quake felt across hundreds of kilometers of islands originate from stresses that have been building silently for hundreds of thousands of years beneath one of the most volcanically active places on Earth? Late on the evening of May 22nd, at approximately 9:46 p.m. Hawaii Standard Time, the island of Hawaii experienced a rare and technically important earthquake that immediately drew the attention of seismologists across the Pacific. The magnitude 6.0 event struck about 7 miles, or roughly 11 kilometers, south of Hononau-Napoopoo, at a depth of about 14 miles, or 22 kilometers, beneath the island. Shaking was reported across the Hawaiian archipelago, with especially strong motion felt along the western side of the Big Island. Residents described intense rolling motion, sharp jolts, swaying structures, and prolonged shaking that lasted long enough for many people to recognize that this was not one of the island's countless small volcanic tremors. Yet almost immediately, scientists at the Hawaiian Volcano Observatory emphasized something critical. The earthquake did not appear to be connected directly to magma movement beneath Mauna Loa or Kilauea. No rapid volcanic deformation was detected. No unusual migration of magma was observed. No eruptive escalation followed. Instead, investigators pointed toward a different and much deeper process: lithospheric flexure caused by the immense weight of the Hawaiian Islands pressing downward on the Pacific plate. That explanation may sound deceptively simple, but the geological mechanics behind it are extraordinary. The earthquake was not merely a fracture in rock. It was part of a massive mechanical response involving the deformation of oceanic lithosphere under one of the largest volcanic loads on Earth. To understand why this earthquake happened and why scientists consider it geologically important, it is necessary to examine how Hawaii itself exists at all. The Hawaiian Islands, over immense spans of time, this process creates enormous volcanic mountains. Mauna Loa alone rises more than 30,000 feet, or over 9,000 meters, from the seafloor to its summit, making it one of the tallest mountains on Earth when measured from base to peak. The total mass of volcanic rock accumulated across the island chain is staggering. That mass exerts tremendous downward force on the oceanic lithosphere beneath it. The lithosphere is not merely crust. It includes the rigid outer shell, composed of crust and uppermost mantle. Beneath Hawaii, the Pacific plate behaves mechanically like an enormous elastic beam floating atop hotter and weaker mantle material below. As volcanic islands grow larger and heavier, they force the plate downward. This bending process is called lithospheric flexure. The mechanics are similar to what happens when weight is placed onto a wooden plank supported at both ends. The plank bends downward beneath the load. The upper portions experience compression, while deeper portions experience extension and varying stress orientations. In Hawaii, however, the scale is vastly larger. Instead of a plank, the structure involved is an oceanic tectonic plate, approximately several dozen kilometers thick. Instead of kilograms of force, the load involves trillions of tons of volcanic rock. This bending creates stress fields throughout the lithosphere. Rocks deep beneath the island slowly deform as these stresses accumulate over long periods. Eventually, the accumulated strain exceeds the strength of the rocks, and faults rupture suddenly. That sudden release of stored elastic energy generates earthquakes. The May 22nd magnitude 6.0 event appears to fit this mechanism closely. According to seismic analyses, the earthquake resulted from oblique reverse faulting at a depth of roughly 22 kilometers. This is an important detail because the style of faulting provides clues about the stress environment responsible for the rupture. Reverse faulting occurs when crustal blocks are pushed together, causing one side of a fault to move upward relative to the other. Oblique reverse faulting means that the motion included both compressional uplift and lateral movement. This combination reflects the complex stress regime produced by lithospheric bending beneath Hawaii. At depths near 22 kilometers, rocks beneath the islands experience enormous pressures and temperatures. These are not shallow volcanic fractures near the surface. They occur within deeper portions of the lithosphere where long-term mechanical stresses dominate. Scientists distinguish these earthquakes from shallow volcanic quakes because their driving mechanisms differ fundamentally. Volcanic earthquakes are often caused by magma migration. As molten rock rises, it fractures surrounding rock, produces pressure changes, and generates swarms of small seismic events. Such quakes are usually concentrated near magma reservoirs, rift zones, or active conduits. They frequently occur at shallower depths and may accompany ground deformation, gas release, or eruptive activity. The May 22nd earthquake showed none of those signatures. Instead, its depth, focal mechanism, and aftershock behavior all matched the pattern expected from flexural tectonics within the Pacific Plate itself. This distinction matters because Hawaii experiences multiple categories of earthquakes, and each reflects different geological processes operating simultaneously beneath the islands. One category involves shallow volcanic earthquakes associated directly with magma transport. Another includes earthquakes generated by flank instability, especially along Kilauea's south flank, where volcanic material slowly slides seaward atop weak basal layers. These can produce large and destructive earthquakes, such as the magnitude 7.7 Kalapana earthquake of 1975. A third category involves deep lithospheric flexure earthquakes, like the recent magnitude 6.0 event. These are tied not to immediate eruptive processes, but to the broader structural response of the Pacific Plate to volcanic loading. The Hawaiian Islands effectively act as gigantic weights depressing the ocean floor. The Pacific Plate bends downward beneath the load and upward farther away from it, producing broad regional warping. This flexural deformation extends hundreds of kilometers beyond the visible islands themselves. Geophysical studies have mapped this bending using seismic imaging, gravity measurements, and bathymetric surveys. Around the Hawaiian chain, the seafloor forms a large depression called the Hawaiian Deep, created by plate flexure. Beyond that depression lies a flexural bulge where the plate arches slightly upward before flattening farther away. This entire structure reflects the mechanical response of oceanic lithosphere to volcanic loading. The stresses generated by this bending evolve slowly over geological time. Each new lava flow adds mass. Each eruption contributes additional weight. As volcanoes grow, the lithosphere adjusts incrementally, but not smoothly. Rocks can store elastic strain for long periods before failing abruptly. That is why earthquakes like the recent magnitude 6.0 event may appear sudden, even though the responsible forces have been building for hundreds of thousands of years. The location of the earthquake south of Honaunau-Napoopoo is also revealing. Western Hawaii Island sits above regions where lithospheric flexure stresses are particularly significant. Seismicity patterns across the island often reflect the combined influences of volcanic loading, gravitational spreading, and structural weakness within the plate. When the earthquake struck, seismic waves propagated efficiently through the dense volcanic and oceanic crust beneath the islands. Hawaii's volcanic rocks can transmit seismic energy effectively, allowing shaking to be felt across large distances. Residents across multiple islands reported feeling the quake, demonstrating the energy released by a magnitude 6.0 rupture at intermediate lithospheric depth. Magnitude 6 earthquakes are not unprecedented in Hawaii, but they are relatively uncommon and scientifically important. Over the past 50 years, there have been 36 earthquakes of magnitude 5 or greater within approximately 100 kilometers or 60 miles of this event. That history shows that the Hawaiian lithosphere remains tectonically active even far from conventional plate boundaries. This challenges a common misconception about Hawaii. Many people imagine the islands solely as volcanic systems dominated by eruptions and lava flows. In reality, the region is also a highly dynamic tectonic environment where gravitational forces, lithospheric bending, crustal deformation, and fault mechanics operate continuously. The 1975 Kalapana earthquake remains one of the clearest examples of Hawaii's seismic potential. That magnitude 7.7 event occurred along Kilauea's south flank and generated a tsunami, major ground deformation, and widespread damage. The earthquake reflected massive seaward movement of volcanic rock along a basal detachment fault. Similarly, the magnitude 6.7 Kiholo Bay earthquake in 2006 caused injuries, structural damage, landslides, and infrastructure disruption across the Big Island. That event also involved deep lithospheric stresses related partly to volcanic loading and plate flexure. The recent magnitude 6.0 earthquake fits within this broader tectonic framework, though its mechanism appears more directly associated with flexural stresses than flank slip. One of the most technically interesting aspects of Hawaiian flexural earthquakes is the interaction between volcanic construction and plate mechanics. As volcanoes build upward, they alter the stress field not only beneath themselves, but throughout surrounding lithosphere. The plate bends downward locally, while deeper mantle material responds viscously over longer timescales. This process resembles isostatic adjustment, though on a volcanic oceanic scale. The lithosphere does not behave as a perfectly rigid structure. Instead, it responds elastically over shorter timescales and viscously over longer intervals. The mantle beneath the plate can flow slowly, redistributing stress and partially compensating for the volcanic load. Yet this compensation is incomplete. Stresses remain concentrated within portions of the lithosphere, particularly where faults or structural weaknesses already exist. Those weaknesses can eventually rupture during stress accumulation. The earthquake's aftershock sequence supports the interpretation of a tectonic lithospheric event rather than magmatic intrusion. Aftershocks following flexural earthquakes usually decay gradually over days to weeks as surrounding rocks adjust to the stress redistribution caused by the main rupture. Volcanic earthquake swarms associated with magma movement often behave differently. They may migrate spatially as magma propagates underground, sometimes intensifying toward eruption sites. The May 22nd event instead displayed more typical main shock aftershock characteristics expected from tectonic fault rupture. Scientists also monitor volcanic deformation closely after significant Hawaiian earthquakes because large seismic events can occasionally influence magma systems indirectly. Strong shaking may alter permeability in volcanic conduits, redistribute stress near reservoirs, or trigger small eruptive changes. However, the Hawaiian Volcano Observatory reported no apparent impacts to Mauna Loa or Kilauea following the earthquake. That observation reinforces the conclusion that the event originated primarily within the lithosphere rather than within active magmatic plumbing systems. Still, separating tectonic and volcanic processes in Hawaii is never entirely straightforward because the islands themselves exist only due to volcanism. Even earthquakes classified as not volcanic ultimately reflect the presence of enormous volcanic masses loading the Pacific Plate. In that sense, volcanism remains the root cause, but the immediate trigger involves mechanical stress accumulation rather than magma transport. The geometry of the Pacific Plate beneath Hawaii plays a major role in controlling these stresses. Oceanic lithosphere cools and thickens as it ages away from mid-ocean ridges. Beneath Hawaii, the Pacific Plate is relatively old and mechanically strong compared with younger lithosphere elsewhere in the oceans. This strength allows the plate to support large volcanic loads while also storing substantial elastic strain. The deeper brittle portions of the lithosphere can fracture during stress accumulation, generating powerful earthquakes even far from plate boundaries. Temperature also influences earthquake depth. In hotter regions, rocks deform plastically rather than fracturing brittly. In cooler lithosphere, brittle failure can occur at greater depths. Beneath Hawaii, the thermal structure allows earthquakes to occur within portions of the lithosphere, extending well below shallow crustal levels. At roughly 22 kilometers depth, the May 22nd earthquake occurred within this deeper mechanically competent zone. The focal mechanism, indicating oblique reverse faulting, further reveals the orientation of stress. Compression associated with plate bending likely produced conditions favorable for reverse motion, while additional regional stresses contributed the oblique component. Detailed seismic inversions conducted after such events often allow scientists to reconstruct the rupture plane, slip distribution, and energy release patterns. These analyses can help identify whether the rupture propagated along pre-existing faults or activated previously unmapped structures within the lithosphere. Hawaiian seismic networks are among the most advanced volcanic monitoring systems in the world. Dense arrays of seismometers continuously record earthquakes ranging from tiny volcanic microquakes to large tectonic events. Data from the recent earthquake will likely contribute to improved understanding of lithospheric stress distribution beneath the islands. The public response to the earthquake also provided valuable scientific information. More than 2,500 felt reports were submitted to authorities. These reports help researchers map shaking intensity across different regions. Variations in reported shaking can reveal how local geology influences seismic wave amplification. For example, softer sediments may amplify ground motion compared with solid volcanic bedrock. Lava flows of differing ages and densities can also affect wave propagation. By comparing instrumental data with human observations, scientists can refine seismic hazard assessments for the islands. Hazard assessment is particularly important in Hawaii because earthquake risk intersects with volcanic risk in complex ways. Infrastructure must withstand both lava flow hazards and strong seismic shaking. Roads crossing steep volcanic terrain are vulnerable to landslides triggered by earthquakes. Coastal cliffs composed of unstable volcanic deposits may fail during intense shaking. The magnitude 6.0 earthquake caused concern, partly because western Hawaii Island has experienced destructive seismic events before. Strong shaking can damage buildings, water systems, electrical infrastructure, and transportation corridors even without volcanic activity. Yet from a scientific perspective, the earthquake also served as a reminder that Hawaii is not geologically quiet between eruptions. The islands remain in constant mechanical evolution. Volcanoes continue to grow. The Pacific Plate continues to move northwestward over the hotspot at several inches or several centimeters per year. New magma continues rising from deep mantle sources. Older volcanoes slowly subside as lithospheric flexure progresses. Faults accumulate stress continuously. Over millions of years, these interacting processes shape not only Hawaii, but the entire Hawaiian Emperor Seamount chain, stretching roughly 5,500 kilometers, or about 3,400 miles, across the northern Pacific. As volcanoes move away from the hotspot, volcanic activity wanes. Erosion gradually dismantles the islands. Eventually, they subside below sea level and become seamounts. Yet even long after eruptions cease, the lithosphere retains evidence of volcanic loading and flexural deformation. The Hawaiian chain therefore records an evolving interaction between mantle plume volcanism and oceanic plate mechanics. Earthquakes like the May 22nd event provide snapshots of that interaction in real time. One reason scientists pay close attention to Hawaiian flexural earthquakes is that they help constrain models of lithospheric strength. By analyzing earthquake depths, stress orientations, and fault mechanics, researchers can estimate how rigid or flexible the Pacific Plate is beneath volcanic loads. This information matters far beyond Hawaii. Similar flexural processes occur beneath other volcanic island chains and large seamount systems worldwide. Understanding lithospheric response to loading also informs broader theories about plate mechanics, mantle rheology, and crustal deformation. The Hawaiian hotspot itself remains an area of intense scientific investigation. Some models envision a narrow mantle plume rising from near the core mantle boundary nearly 2,900 kilometers, or about 1,800 miles, beneath Earth's surface. Others propose more complex plume structures involving interaction with mantle convection currents. Regardless of the plume's exact geometry, the surface expression is undeniable. Massive volcanic construction has altered the Pacific Plate profoundly. The recent earthquake represents one consequence of that long-term loading process. Modern geophysical imaging techniques continue improving scientists' understanding of these systems. Seismic tomography can map variations in mantle velocity beneath Hawaii, revealing regions of hotter or partially molten material. Gravity studies measure density contrasts associated with volcanic structures and lithospheric flexure. GPS networks detect subtle ground movements measuring only millimeters per year. Together, these tools allow researchers to monitor how stress accumulates and evolves beneath the islands. Still, predicting exactly when earthquakes will occur remains extremely difficult. Flexural stresses may build gradually, but fault rupture depends on complex interactions involving rock strength, pore pressure, fault geometry, and stress transfer from previous earthquakes. The May 22nd earthquake likely altered stresses on nearby faults as well. Aftershocks represent one expression of this redistribution. Some faults become closer to failure after a main shock, while others experience reduced stress. Understanding these interactions is essential for assessing ongoing seismic hazard. Although aftershocks following a magnitude 6 earthquake are usually smaller than the main event, they can still pose risks, especially to already weakened structures. The absence of direct volcanic involvement in this earthquake does not reduce its scientific significance. In many ways, flexural earthquakes reveal deeper and slower geological processes that are harder to observe than eruptions. Lava flows provide dramatic surface evidence of volcanism, but the bending of an oceanic plate beneath trillions of tons of volcanic rock unfolds mostly invisibly over immense timescales. Earthquakes offer one of the few direct windows into that hidden mechanical system. The Big Island remains the youngest and most volcanically active island in the Hawaiian chain. Kilauea and Mauna Loa continue adding material to the island, increasing the load on the Pacific plate incrementally with each eruption. Over geological timescales, that means lithospheric stresses will continue evolving. Eventually, the locus of volcanism will migrate southeastward as the Pacific plate continues moving northwest. New submarine volcanoes are already forming offshore. Loihi Seamount, also called Kamehameha, represents the next stage in Hawaiian island development. As it grows, it too will contribute additional loading and flexural deformation to the lithosphere. Thus, the recent earthquake is part of an ongoing planetary-scale construction process driven by mantle heat, plate motion, gravity, and rock mechanics.